Hello YouTube. Today we'll be going over some mechatronic practice problems. More specifically, we're going to go over how to find state equations and find the transfer functions from those state equations. So, if you're watching this video, some things you should be familiar with. I call this my toolbox for bond graphs and dynamic systems analysis. So you have to already know what bond graphs are, what 0 and 1 junctions are, common flow, common effort, derivative causality, anything pretty much on this piece of paper here in this picture. If you do have an idea of what I'm talking about here, then I'm pretty sure you have seen something like this before, where you see a bond graph. And rather than trying to determine a bond graph or find a system that represents in the mechanical, hydraulic, or electrical domain, here we're asked to find the transfer functions. To find the transfer functions, we're first going to need to find the state variables. The transfer functions are simply the state variables divided by the input. In this case, our source of effort is f of c, and we have two state variables here, which are p and q, that are on I and c respectively. And so our state variables, like I said, are I and P, Q and P, and our input, was our source of effort, is our f of c. Now our state equations are written in terms of the state variables and inputs. So when we write the state equations, when we derive them, we have to make sure that they have f, c, q, and p in there. There can't be anything like a p, or like a flow from R2, right? Okay, so let's write the state equations, and with the ultimate goal of finding the transfer functions. So, let's start with P dot. So P dot is related to effort. Since P dot is the time derivative of momentum, then we can say this is a one junction, and if you look at the toolbox over here, one junctions have common flow, and their efforts sum. So that means effort is a sum, and in this case, we're subtracting E1 or E2 and E3 from E1. Notice how P dot, the arrow is going away from the one junction, so that means whatever comes into the one junction is positive, and whatever goes away from the one junction is negative for this case. So that means E1 is positive, we're minusing E2 minus E3 from that. Okay, well now we can write E1, E2, and E3 in terms of their flow and effort general variables, right? So E1 is FC, that's our input. That's exactly what we want, so perfect. We have nothing to do there, we just write FC. Now E2, okay, so let's look at the capacitance over here. Notice how E can be written as 1 over C times Q. So we're like, okay, I'm looking at the wrong one. We're looking for flow, right, equals 1 over C times Q. But that's for E3. So for E2 would just be R times F2, because if you look over here, look at the resistance, you can see E is equal to F times R, and I just rewrote it as R times F, and then, like I said, 1 over C times Q for E3, looking at that toolbox. Okay, so since we know that at a one junction all the flows are common, that means F2 is equal to F4, and that means F2 is simply 1 over I times P. And we know that because we know for the inertia there on the top left, we have F equals 1 over I times P. Now the reason we are looking for, P, we're looking for P, is we want the equation to be written in terms of the state variables and the inputs, correct? So now we can put everything together, and we're like, okay, we have FC for E1, E2 was R times F2, which F2 can be written, as we said here, 1 over I times P, and then we have 1 over C times Q. Look, we have P, Q's, and our inputs, and we have our coefficients in front of each of those state variables. Now, the state variables actually have more of a physical application here, which are written there. We have I for M, B for R, and 1 over K for C, so we can write that more specifically as the following equation here. So boom, we got our first state equation. Now let's find the second one. So the second state equation is relating to displacement, or the time derivative of displacement. And that is related to flow, right? The derivative of the rate of change of a distance is velocity, so we're looking at flow, right? So at a one junction, all the flows are common, so we just set it directly equal to F4 because we want it in terms of the state variable P. So we have, and we know for I, looking at our toolbox again, F is equal to 1 over I times P, so that's how we get Q dot is equal to 1 over I times P. Boom. And more specifically, we know I is equal to M, so boom, we have our second state equation. Now, in order to write the transfer functions, we're going to do a little trick. First, we're going to put the equations, the state equations, into matrix form. And the matrix form looks something like this. X dot is equal to matrix A times vector X plus matrix B times vector U. And we'll write it like this. So X dot is simply the rate of change of our state variables equals to the coefficients of our matrix, which we'll get to in a second, times our state variables, right? Plus, which are P and Q, plus the coefficients for the input matrix, which is F of C. So we separate our inputs from our state variables, right? Because our state equations are written in terms of state variables and inputs. So now let's look at the equations. So let's look at P dot. Is there any term in there that has a P in it? Yes. So we say that's negative B over M. Oh, real quick. We notice that there's a input effort, which is 1, right? Because there's a FC in the P dot equation, so it means we put a 1 coefficient of 1 in front of it. And there's not an effort input in Q dot, so it's just 0. And now we move on to the coefficients again, so we just said is negative B over M. And then, is there a Q in the P dot equation? Yes, and that coefficient is negative K. And then now let's look at Q dot, which is simply 1 over M times P. Is there P in there? Yes, 1 over M. Is there a Q in there? No, so just 0. Alright, so now that we have our equations in matrix form, we're going to use a technique called Cramer's rule to solve for the transfer functions. And this is a linear algebra technique. Pretty much it's a mathematical trick to invert a matrix when the matrix is kind of difficult or complicated to do by hand. So we're going to look at the S domain here, where you know S times the identity matrix minus A is the determinant, right? So we're going to take a look at the determinant of SI minus A. So let's rewrite our matrix in the S domain. All you do is add S's in the main diagonal, and then make sure you flip the signs of the coefficients. So we have negative B over M becomes plus B over M, negative K becomes negative 1 over M becomes negative 1 over M, and negative K becomes positive K. And we're going to continue to have our P and Q matrix, and we set that equal to our inputs. And Cramer's rule is, I'll have this piece of paper over here that kind of makes an easier example. I'd suggest you pause the video and kind of possibly do this example yourself. But pretty much you take you take your matrix, you take the coefficients, and you put them in your X or Y column, and you solve for that by taking the determinant of each of those 3 matrices, and then do the ratio of the X to the original matrix, and then the determinant of the Y to the original matrix, and then you can get your answer there. And a review of the 2x2 matrix determinant can be found below, as well as the 3x3 determinant. So, going back here, let's set up our equation for P over FC, and that's our first transfer function we're looking for, right? So the ratio of output to input, right? So we have, let's look at our first equation. How we're going to set that up based on what we see here, right? So we have the determinant of our matrix, right? We're going to put our coefficients, since we're going to call this the X term, like X and Y, pretend P is X and Q is Y. So since we're looking for the P term, we replace the P column with the coefficient. So it's 0 and 1, right? Now we leave the second part alone. It's going to be the same, S and K. We're like, okay, we got that. The bottom is just going to be the determinant of SI minus A right there. Just the matrix we have right above that. So we leave that, and we do the determinant, which can be found using this formula AD minus BC. Is how you calculate the determinant for a 2 by 2 matrix shortcut. So we have S times 1 minus 0 times K, and then for the bottom one we have S times the quantity S plus B over M minus the negative 1 over M times S, or that should be K. I didn't fix that, so that's an error there. So that should be, instead of an S, it's a K. Okay, so forget that. Now let's look at, so our final answer would look like this. So this error fixed the mistake. So that's our transfer function. Boom, we found our first transfer function. Great. Now let's find the second one. So the second transfer function, recall, is Q over FC, which is simply the state variable over the input. And using Cramer's rule, we know we can write the determinant of our matrix by replacing the coefficients of the input in the Y column while leaving the X column from the original matrix the same. So that's the X column from the original matrix, and then we put the coefficients there. And when I meant by original, I meant the SI minus A matrix. Now, the bottom is the denominator is the same as the denominator is this last one. You keep those the same, just as it says down here. Determinant of D, those are the same matrices. Take the determinants, and we get 1 over M and over S squared plus B over MS plus K over M. Boom, we found our second transfer function. We did it. That's awesome. So now we're like, okay, we found our transfer function and our second transfer function. Boom. So when you're given, in summary, when you're given a bond graph, or when you find a bond graph, you first need to figure out their state variables and their inputs, determine the state equations. To find the transfer function is simply the ratio of the input to the output to the input. So state variable over the the sources. And then when you have your state equations, which you know how to derive from the bond graph, then you can put the state equations in matrix form and use Cramer's rule to solve directly for the transfer functions. And Cramer's rule we're using is because it's an easier trick to invert the matrix for more complicated systems. So I hope this example helped. I know these problems get a little long, a little tedious, and I figured that this would be a good example to kind of combine determining state equations as well as finding transfer functions, which are more applicable for analysis. All right, well, I hope this example helped, and good luck and happy studying.